Hello everyone, hope you are all fine in the confinement. So sorry for being late. For the previous few days, I was preparing something else. So now I will be uploading videos in regular interval for your tutorial. So today, in this episode, I'll be discussing the preliminary or recapitulatory portions of electrostatics to further proceeding towards uh, method of images. First of all, we should recapitulate the basic concept of potential. Earlier, we have discussed lots of problems and theoretical aspects of electrostatics, especially Gauss's theorem, Coulomb's theorem, conservative measure of electric field, electrostatic electric field, and so on. So today I will be talking about potential. You should not be confused about the potential, electric potential, with the potential energy. Both are different. I will be discussing the difference in the next classes. Uh, Today I will be discussing only on first in this episode only on potential, electric potential. Now, why potential? There is a field we have studied due to electric charge, and that is electric field of conservative in nature. So electric field is a vector quantity, and you know very well that life becomes very tough, especially mathematically, when we deal with vectors. So to make life simple, we have a method or a process or a tool, that is to convert a vector into a scalar. A scalar is very trivial and easy to handle, very well. Now this is how potential concept is formed. Not only that, it is because of the conservative test nature of the electric field which made our life very easy. So first, the electric field. The static electric field, I'm not talking about any time dependent electric field, just static electric field, that is only space dependent. So for example, we have an electric field E equals to xj. This is a vector field. Okay. So whether it is conservative or not, if you take curl of this vector, you may not get 0. You don't get 0. So this is not a conservative field. Now, if we think of something that is conservative in nature, then we can have the concept that the work done or the line integral is always path independent, isn't it? So for example, we have a reference point here A and another reference point here, it is B. So suppose we are considering two paths, path 1 and path 2. So as this is path independent, so we can think that the work done to, or the line integral of the vector E or electric field via this path or that path will be different. It is not different. So we know that E dot dl equals to 0, or from A to B via path P1, for example, P1 minus E dot dl is A to B E dot dl, okay, via path P2. So far so good, this is trivial. Now if we think a scalar function which is based on this concept that it is path independent scalar function, that is V function of R only the position, not the path, that is E dot dl from any arbitrary reference frame to any position R. So this is the potential, electric potential. Now if we consider the potential difference between those 2 points A and B, that means V of B minus V of A. From the concept of gradient, we can say that this is nothing but grad of V dot dl from A to B. Okay, this is the primary definition of gradient. So from that point or that equation, we can say that V of B minus V of A equals to minus A to B E dot dl. Therefore it is path independent, so any arbitrary reference point we have the choice to take any arbitrary reference point. If you differ, suppose someone is taking reference point 1 and someone is taking reference point 2, so that difference does not make any change, okay, because another constant term will be added and which will be cancelled. So that is not our concern. So from these two equations we can easily say that E equals to minus gradient of V. So this is the differential form of an electric field in terms of a scalar field. So this is the relation from a vector to a scalar. Okay, happy? So if we think the Gauss's theorem, from that point we can say that we know that divergence of E equals to rho by epsilon 0. Is it? Not rho, actually this is the integral form of rho. So using this equation we can say that del square V equals to minus rho by epsilon 0. Fine. So equation is nothing but Poisson equation. The interesting part is not here. It is also very interesting because this is a scalar second order differential equation. So we have the experience previously that how to deal with this kind of equation and how to solve it, how to resolve it with certain boundary conditions. That may be Neumann or Dirichlet, whatever. So if we think there is no charge, no free charge, what will happen? This term will go to 0. This is Laplace equation. Now, if you think or look into this equation, it is evident that whatever the condition, that is maybe the no charge is there, no presence of charge, still there is a solution for the potential. So, no charge is not essential to construct any potential or have any potential. You can easily solve it for certain boundary condition and have the solution. Maybe oscillatory solution or sine wave or whatever, depends on the boundary condition. So this is the primary concept of field. So without any charge, field is also possible. So this is the basic concept of potential. In the next episode, I will be talking about the method of image. Okay, so wait for next episode.